absorption spectra of transition metals, if I remember correctly. So whenever you're ready, please start.
Can you hear me?
Yes.
Okay. Thank you, organizer, for giving me this opportunity to present my talk today. So today I'm going to talk about X-ray absorption spectroscopy of solvated transition metal ion and the performance of wave function, multi-reference wave function theory and density function theories in computing those spectra. To talk about the importance of X-ray spectroscopy, I think many of you are aware nowadays X-ray spectroscopic technique are becoming more and more popular to characterize different materials and chemical species. Specifically because the core level spectroscopy or X-ray spectroscopy actually gives us excitation for core orbitals that are very localized. So if you want to know about the local electronic structure of a particular atom, then this is a very useful technique. So from this spectroscopy, you can get information about the oxidation state, spin state, or chemical bonding of a particular atom. Then you can also get information about the solvation structure around the metal center. Since you have all this information, if you have good enough technique, you can actually monitor this, the change of the electronic structure or the solvation environment during a chemical process, and you can see how this different information of changing with the chemical reaction or chemical transformations. Now, X-ray absorption fine structure spectroscopy is particularly interesting because it gives a lot of information about local solvation structure of particularly metal center. These are important for studying enzyme, catalyst, and all that. And X-ray absorption fine structure or XAFS has two different regions. So one region is X-ray absorption near edge spectroscopy or XAFS, and then extended XAFS. Now, X-ray absorption near edge spectroscopy basically involve the core to valence transition. So these are transition to valence and near valence orbitals, and then you have extended XFS, which are higher order excitations. So these core to valence transitions, they mainly contain information about the electronic structure of that particular atom, from where the core excitations is happening. And we are in this particular study, we are actually interested in that part of the spectrum. Now, for obvious reason, many people wanted to study ZAs of solvated transition metal ion, because as we know, transition metal ions are very abundant in spectroscopy, in transition metal catalysts and metal enzymes and many other areas. But one problem that we noticed when we looked through the literature, the good experimental spectra were not available for many of the first two transition metal ions. Even when they were available, you cannot compare them because they were done in different environment, and they were done in presence of different counter ions. So the counter ions, if they are very strongly connected with the metal ion, that will affect the solvation environment. And if you are not using the same counter ion for all your studies, then you cannot really compare them. So this was one problem that was there. And then we saw that some of those experimental studies also perform theoretical study, but many times the results didn't match, and they didn't go into the details why sometimes theory is failing or not giving the giving proper results. So we wanted to do a very systematic study for all the first two transition metal ions for experimentally, and then try to explain those spectrum using theory. So these are the ions that we want to study. So we wanted to start from vanadium 2+, 3+, and go up to copper 2+. Zinc 2+ doesn't have any vacuum orbital, so we are not interested in that. With the help of our with our experimental colleagues from Pacific Northwest National Lab and University of Michigan, we were able to get Zanes for all those metal ions. in water, and they have used ClO4 minus, which is a very weakly interacting counter anion. So, so we can say that these metal ions are almost free in the water environment, and whatever we are getting the spectra is due to the metal ion. There is not much effect from the counter anion. So as you can see, there are a lot of features that we are getting in the experimental spectrum, and our job as a theoretician was to see why certain peaks are appearing in one ions and not appearing in the other, and what are the nature of those excitation. So first thing that we have to do, we have to get the structure before we go to the excited state. So one thing that we did is to optimize, perform a DFT based optimization. We took 40 explicit water molecule around the metal ion, and we also put Cosmo solvation to take into account the long range solvation effect. And we optimize the structure. And as you can see from extended XAFS, we can actually get the metal oxygen bond distances. And what we got from experimental spectra and what we got from theory, when we compared, we did very well. Our computed structures were very close to the experimental ones. There were some discrepancies, like the equatorial, the axial bond distance of copper, which is more elongated because of the entropy distortion. So those are the kind of discrepancies that were still there, but in most cases we got very good results. So we used that structure to perform excited state calculations. So first we perform TD-DFT calculations with PP0 functional. And as you can see, if we go from manganese 2 plus to copper 2 plus, this column B and C, actually TD-DFT performs very well, and more because these are mostly single excitation, so there TD-DFT has no trouble. But we saw in two cases, particularly in vanadium 3 plus and chromium 3 plus, if you see vanadium 3 plus also TD-DFT is doing perfectly fine, but there is this small peak that TD-DFT doesn't get. And for a while we thought maybe this peak is coming because of the vanadium 4 plus impurity that is there, and we cannot eliminate it experimentally. Maybe it's since our theory is not getting it, maybe it's not there in the actual vanadium 3 plus spectrum. And then in chromium 3 plus, the problem is actually much severe. You can see this splitting between these two peaks is much larger compared to what we get in TD-DFT. And this was also reported in one of the earlier study, and their theoretician didn't try to explain why this is happening. And there is another thing that is there in TD-DFT, and people who have performed X-ray spectroscopic calculation with TD-DFT is that if you want to align your theoretical spectra with experimental spectra, you have to use the empirical shift, and those shifts for organic molecule can be 10 eV, 10 to 20 eV, but for transition metal they can be hundreds of eV. For in these cases, we had to use you can see the shifts here, more than 100 eV shift to match the align experimental spectrum with our computational spectrum, computed spectrum. So that error was also there. And one of the reasons that I think everyone knows that in TD-DFT we have the ground state is single state determinant. But I think more important here in this particular case, many of the error is coming because we don't in TD-DFT we don't consider any of the higher order excitation. So if those are contributing to any of the peaks, then we are not going to get it correctly. And then this large shift mainly coming, many people have attributed it to self-interaction error of the exchange correlation functional. And then we are also missing orbital optimization in the excited state because it's a response theory. So all these are contributing to this large empirical shift that we have to use all the time in TD-DFT for X-ray spectroscopy. So I wanted to move towards multi-reference calculations, and for that, first I have to reduce the size of the system. So what I did, I took the hexacoordinated metal ions, so just the 6 water molecules that are connected to the metal ion. I took that reduced system, and then to take into account some of the solvation effect, I replaced all the water molecule with the Cosmo point charges. So this is not the ideal case, but this significantly reduces the cost of our multi-reference MCSCF of our PT2 calculation and takes some effect of the environment of the solvation. And when I perform MRPT2 calculation, so you can see here this the spectra here. So this is our active space. So we put one S in RAS1 and all the 3D orbitals in RAS2. We don't have any of the ligand oxygen or ligand water orbitals in our active space. And again, for MRPT2 also does fairly well for the column B and C, as good as TD-DFT. But for vanadium 3+, now you can see this experimental peak that we were missing in TD-DFT. It's now there for MRPT2. And from chromium 3+, the splitting between two peaks is now significantly higher. And what we have observed when we looked at the wave function that are responsible for these particular peaks that were missing or which were underestimated in these cases, we saw that there is a certain type of excitations that are involved, which are kind of double excitations. So you get this double or higher order excitation actually. So you get this excitation from 1s to 3D, and there are some rearrangement involved between electrons that are there in the 3D orbital. So this type of excitation you cannot get from TD-DFT, and those are the one actually the reason for the missing peak and all the underestimation of splitting that we were getting. Now, we also saw that we have some improvement over TD-DFT when we looked at the empirical SIP that we needed for MRPT2. Now you can see we are actually below 20 eV for most of the metal ions. Highest is for nickel 2+, which is 21 eV. But we were for TD-DFT, the SIP that we needed was more than 100 eV. So MRPT2 also corrects the absolute value that we get for individual excitation, which is also promising. But then if you see these systems, we are lucky because we don't have to consider any of the ligand orbitals. So our active space is significantly small and we can perform MRPT2 calculation. But we want to see if we can do something cheaper. So I have used multi-configuration pair density functional theory. I don't want to go into the details because many of the original developers are here in the audience. But just for the people who doesn't know, in this theory, actually the kinetic energy and nuclear attraction energy is calculated from is obtained from MCSCF. And that the multi-reference density is used to calculate the classical Coulomb energy, and then everything else like exchange and correlation is calculated from on top pair density functional, which is a new type of functional translated from Kohn-Sham density functional. So when I use this, and particularly I was interested in vanadium 3+ and chromium 3+ because those were the most complicated system that we had. And you can see if you compare RAS-PT2 and MCP-DFT, they are actually very close in both the cases. Actually, in chromium 3+, I would say the MCP-DFT results were even better than RAS-PT2 because first two peaks that we get in RAS-PT2, the splitting is actually higher in that case than what we get in the experiment, but MCP-DFT gets it very well. And then, so what we can say that MCP-DFT or the TPV, translated PV functional, does as good as or even better in some cases than RAS-PT2. And if you look, one of the reasons that I think this is the success we are getting in MCP-DFT, and it is irrespective of the results, it is an interesting idea to use this theory for X-ray spectroscopy, because first of all we get multi-reference ground state, and then we are including all type of excitation at least within the active space. So if it is if in a certain type of spectrum multi-excitonic states are important, there this theory will do much better than TD-DFT. And then at least at the wave function level, this theory doesn't suffer from self-interaction error like TD-DFT. Because we are getting the wave function from MCSCF theory. And since we are performing a state average calculation from the excited state, at least the excited states are optimized. At least we are getting an average optimized orbital for excited state at the MCSCF level, and that we are using that at the MCP-DFT level. So we are getting some amount of orbital optimization at the excited state, which is also contributing to the less error of MCP-DFT. And we can see though all those effect when we look at the absolute empirical correction that we needed. We still need the correction, which also interesting, but the correction needed is now significantly small. Actually, in most of the cases, the correction needed for MCP-DFT is less than 10 eV. And you can see we are doing better than PT2 in those cases. So in summary, we have provided actually a systematic study of K Zanes for first row transition metal ions. And then we have used SPT2 and TD-DFT to show that there is an interplay of single and multi-excitonic state, not only double, there are higher order excitations that are present in those spectra. And then we have shown that the MCP-DFT can be used as an alternative to RASPT2 for X-ray spectroscopy study. And I would like to acknowledge my collaborator. This is a multi-institutional effort. Our experimental colleagues are from PNNL and University of Michigan. And then our theoretical colleague are also from University of Irvine. I started this project in Pacific Northwest National Lab, and I finished it when I joined as faculty in